Hello, welcome to the Hitchhiker's Guide to the Machine Learning Engineering Galaxy. So, what do we have on our agenda for today? Of course, we start with introduction. You need to know whom you're talking to. And then we go to discuss what's the difference between traditional and AI-powered software. Then we move to MLOps, and it's exactly machine learning operations. And then we finish with some hands-on with machine learning serving pipelines. We'll discuss batch serving, we'll discuss online serving in real time, and we're going to discuss real-time serving with embedded model. So let's start. So the introduction part. Who am I? And once again, why do you need to listen to me? So my name is Alyona Galyeva. I'm working at Linkit as AI and data engineering lead and one of the principals. But that's not the thing that I just doing at Linkit. There are a lot of things that I do in my spare time, and it's exactly two things, or three. Three. So first of all, it's my non-profit, PyLadies Amsterdam, and it's exactly about promoting Python. And what we're doing every month free of charge Python workshops. And it can be about data science, machine learning, or something unrelated, such as web development. From the other side, I'm as well an AI and tech mentor for the AI Accelerate program. And this is a program for, in combination with Startup Amsterdam and other companies, to support female entrepreneurs in the field of AI and data. And the third, I really love to do some things with my hands, and from time to time I build the sensor on my own and then experiment with the sensors. Okay, now you know who am I, so let's discuss what the difference between traditional and AI-powered software. But before we start, I would like to dig a little bit deeper into what AI means. And AI is a really broad description. And we gonna discuss today on a small subset of AI, and it's exactly machine learning. We'll touch deep learning as well a little bit, and deep learning, this is a subset of machine learning. And when you hear machine learning, it's always goes around four components. We always talk about model, data, feature, and predictions. So let's deep dive a little bit about it. So what is exactly the machine learning? Machine learning is the process of training or building models that learn some patterns from data. And if you take a look at model, what exactly it is, it's just an algorithm. That's mathematical computation. And this algorithm learns a solution to a problem from a specific sample of data. So when you hear something like model and algorithms, you can use it in the context of machine learning interchangeably. Then we talk about data, and data can come in various formats. And if we think about the data that I used to train machine learning model, it's mostly structured or unstructured data. If I'm saying structured, think about numerical and categorical, or think more about like a tabular format where you have columns, where you have specific rows. So for numerical, you, of course, talking about integers, floats, and other numerical values, and the categorical is more about things that can be split into categories. And if we're talking about unstructured, it's more about text, audio, images, and videos. Wait a second, can you say? But text is as well, it's a sequence of characters, so it's structured as well. Yes, but before you use it for something, let's say, meaningful, you need to make sure that it can be properly understood and translated into the machine world. So that's the model, that's the data. And then we talk about features. And maybe some of you heard the word feature engineering. So what exactly feature is? Feature in this case is just an attribute that is useful or meaningful to your particular problem. I will try to give an example. So imagine we try to predict the price of the house. In our case, we're working with structured data. So we have, let's say, like a table where we have as a columns some specific features, and in rows some specific values. Example of the feature can be distance from the city center, number of bedrooms, the square meter, the number of square meters for your house. So this can be a feature. If we take a look, for example, at text, what will be the feature here? It can be the number of stop words or something different. So that's other features. So in this case, you take a data, you process data, you choose features, we call this feature extraction, and you can do it manually, or you can use other techniques to extract features in an automatic way. And based on those features that is meaningful, you try to model the world around you, you try to model the problem, and that's where your model comes into place. And then you have a prediction, and that's exactly when we send into a model sort of on unseen data, and the model returns an output, and that's exactly what we are waiting for. So once again, if we talk about machine learning terminology, we will talk about the data that can be structured, unstructured. We talk about model, that exactly the algorithm that learns a solution to a problem from the specific sample of data. Then before inserting data into the model, we need to transform and preprocess it. That is the feature engineering piece. And then as an output, you got a prediction. So if I want to say it really, really simple, think about model as a big function. As an input, you have data with features, and as an output, you have a prediction. So you think about that, okay, as soon as machine learning starting to spread all over the world, why exactly it's happening right now, and why was it here before or not? And are there any roles, engineering roles, and other roles that pop up with the development of machine learning? Yes, of course, AI was here for more than 60 years ago. But before that, the compute was so expensive that if you want to prepare or train a specific model algorithm, you need to wait for ages. And it was really, really expensive. And now, with the cloud, we have a really cheap compute available, and as well, we are not limited by storage anymore. So now, with the migration to the cloud, you got an enormous resources to do a lot of different analytics, processing, and analysis. And about the new roles, when we talk about the machine learning ecosystem, now probably you heard about data scientist, data engineer, machine learning engineer, research scientist or machine learning scientist, data analyst, and the broad term is developer. So here, just a brief description of each role. So a lot of people heard about this magical unicorn data scientist. A person has vast knowledge in math, statistics, and programming, and design of the systems. But frankly speaking, in this case, the data scientist, this is the person who is responsible for first exploring the data and doing exploration and statistical analysis on the data to understand whether this data is useful, whether this data is meaningful, then perform a sort of feature engineering if it's necessary, and then try to choose the best models and find the best way to find the model that corresponds exactly to the solving of a particular business problem. And the goal is not to build a model, the goal is to find the solution to your problem. Then you have a data engineer, and data engineer is a person who is responsible for data infrastructure and data pipelines around it. Why this person is necessary? Imagine that you're working for a company and you want to help your marketing department to do something. Then in this case, you probably had different sources of the data, and it can be SQL database, it can be some API, it can be some data warehouse where you need to extract data. Sometimes all this data come in various formats, sometimes there are duplicates. So the best option, if you have a data engineer who can help you to bring data from A to Z and transform them in the way that is useful for data scientists to work further on. Then you have this interesting candidate as a machine learning engineer. And this person is exactly responsible for model pipelines and model infrastructure. So to make sure that the model that was chosen, trained, evaluated by a data scientist is ready to be used. And then you have a research scientist or machine learning scientist, and this is exactly the person who comes up with new algorithms. The data analyst is an old traditional role, and it's more the person who helps your company to get insights from structured data. And that's why exactly many years ago the data analyst was enough when you have your SQL database, and the data analyst can do some SQL queries, get insights, and generate some BI reports, for example, some simple dashboards. And now in the world where we get more and more and more data, and it's from different sources in various formats, that's where the data engineer shine. And this person helps you to make sure the data are in a digestible way and they are ready for further analysis by data scientists and data analysts. And of course, I have a developer, software developer, who's responsible for the production system that the company runs. And together, in collaboration with data scientists, data engineer, and machine learning engineer, we are building the production system that can use our model, that end users can access the model and get value from it. So that's a little bit about the roles that are there. But now you want to ask me, okay, you're telling me all this, it sounds really, really complex, you have some strange things like machine learning, okay, there are a lot of new roles pop up in the market. Okay, but what's the biggest difference between traditional and AI software or AI embedded software? And once again, I use interchangeably AI and ML. In this case, we are talking mostly about ML, about machine learning. So if you can see the picture, then from the left side, for the traditional engineering, you have the code that you need to version. That's pretty it. It's really simplified version of it, but that's it. That's what you have. In case with AI software, you need to version 4 components. You need to version the code, you need to version the data, you need to version the features, you need to version the model. Wait a minute. Why on earth do we need to version all of it? Why can't just take the piece of code and it will be enough? The issue is that in machine learning world, we are not using logical rules. In case of traditional software, you have a specific rules. Based on these rules, you know what to expect out from your software. In case with AI software, there are a lot of stochastic things happening. So sometimes we try to make it as reproducible as possible, but it's really hard because a lot of elements playing, and that's why we don't use the pure logic here, but we take sample of data and we look for patterns in this data. And if we change the data, it means the features will be changed as well. And it means that the model will be changed as well. So it's dependency. The data changes lead to feature changes and lead to model changes. And everything should be represented, of course, in code. So these 4 elements. Some companies just try to version code and then they learned in the hard way that if you do just this, it's a little bit too late. So the best practices, if you start your journey with even experimenting with ML, always think about how you're going to version your code, data, features, and model. And more to it, if you just heard that in comparison with traditional software, there are some specific roles, some specific algorithms. You need to version a lot of things at the same time. For the production system, what is the most important? It's that all tests run properly, and then you can monitor everything properly in production. And that's where it is the hardest time, because for traditional software, you're moving from unit test to integration test, and then the other type of test, and you have like the code, then you have something at the output, you have the running system in production, and you do the system monitoring, you know what to expect. In case with ML, you need to do even more. So instead of just unit tests for code, you get data test, then you get a feature test, you get a model test, you get as well a machine learning infrastructure test to make sure that your environment is always reproducible. Then any changes of the data and any statistical changes of the data. And then if we're talking about the monitoring, yeah, of course, you know it, we need to monitor on different levels, of course. So we have a system monitoring, we have a data monitoring, we have including feature monitoring, and we have a prediction monitoring. So it sounds really, really, really complex, but hold on, we go through it. And if you look at it, what are the common machine learning challenges? The biggest challenge is the data quality. And as always, there is a proverb in a traditional software world, garbage in, garbage out. So in our case, with data quality, if you have a really terrible quality of the data, your model will never deliver something qualitative and good. Garbage in, garbage out, as simple as that. In this case, you want to make sure that your data is accurate, that your data is complete, that your data is consistent, and your data have specific timeline. Then the second challenge is reproducibility. As I mentioned before, the machine learning models, they usually inherit some element of randomness. For example, while you train a deep neural network, you need to initialize weight, and sometimes you do it randomly. So how can you ensure that next time you can give the same results back? Then you have the challenge of data drift. So your data can change over time, and just, the simple example, the COVID situation. Take into account all predictions that were made before COVID, and then how COVID drastically changed the majority of the data. Think just about the parcel delivery. How many parcels were delivered before COVID and how many parcels delivered now? Think about other prices or something related to it. So data tends to change over time. Then there is a scale, and exactly we want to know how to scale the whole infrastructure around the models properly. And the last and the most important is that while we're trying to use machine learning to solve particular challenges, that's exactly the multiple objectives that we pursue. And in this case, it's an art of balancing or what to optimize. And what do I mean by that? As a data scientist, you want to optimize for specific performance of the model. At the same time, as a business manager, you don't care about performance of the model, but you care about the results that you can get with this model. And then if you see it from perspective of the security, it's completely different objectives. So the common challenges are data quality, reproducibility of the results, data drift, scale, and multiple objectives. So, you heard a lot about the complexity of the problem, about so many new roles, so many new things, and the question, what I'm going to do with all of this? And there is where the MLOps, or machine learning operations, plays a role. So let's look together through the world of MLOps. And if you want to know what is simple what it is, think about like DevOps, but for machine learning. And 1 minute back, it was 4 things that you need to version: is your code, is your data, is your features, and is your model, sometimes without features, sometimes with. And it requires a specific infrastructure and specific tooling around it. Unfortunately, there is no one standard so far. That's why there are millions of offers pop up in the market. And if you just look at the number of libraries that pop up and the number of tools that pop up, it's tremendous. But they all try to follow almost the same story. So usually you start with the manual processes. When we talk about the machine learning, there is 2 almost separate things. First, it's a lot of work, it's a lot of iterative work when you go through the data, you pick up specific features, you transform the data, you clean the data, you pick up the specific algorithm, you train your model on it, you evaluate your model, you validate your model, and if it returns something that is expected, then you say, okay, this is the trained model, and this trained model I want to use in production. So the whole process of model training, it's a little bit tedious. It has specific steps, but these steps are not specific in sequence because sometimes you did some data preparation and understood that's completely something that you don't want to see. You need to go back, you need to find the new data, or you need to process data differently, or you need to pick up completely different features. So there is a lot of things happening. And it's not in the circle how a lot of diagrams showing it up. It's exactly made 1 step, maybe step back. Made 2 steps, maybe 1 step back. So if you're doing it all of it manually, it's really tedious and it's really error prone. So in the majority of the cases, the data scientists will be working in the environment of the Jupyter notebooks. And there are pros and cons of using them, of course. They're really great for experimenting. They're really great for good visualizations, but sometimes it's really hard to deploy them in production due to some reasons. Of course, there are pros and cons, but in the majority of the cases, that's the story. On top of it, imagine that your company has everything in Java or in other languages. And the data scientists work in the majority of the time in Python or R. Why? Because these two languages really could support all the algorithms. I know that some of you will be saying, oh, Python is slow and this. Of course, yes. But what I'm trying to say that sometimes there is a clash between these two words, because you have a sort of Python ecosystem that completely stand out from the whole ecosystem of your company. And you need to find a way how you can pick this model and make it compatible with your current infrastructure and your current languages that you're using in production. So if you look at the first level of MLOps, it's just a manual process. So there are some steps that you're trying to do in this, let's say, development sandbox. And then as a result, you are taking a trained model. And this is your artifact. And it can be a serialized model. It can be the whole pipeline, including data pre-processing and output post-processing. And then you want somehow to probably register this model in a sort of model registry, and then serve this model, and then use there are different ways how you can do it. But this is really tedious and error-prone mode, because every model degrades every day in production. So imagine if you notice that something wrong with it, how fast you can get another model in place of it, or how fast you can follow the same steps to do some little improvements. So in this case, everything happening manually. There is no triggers that trigger retraining of the whole model. There is no, let's say, clear and ready-made pipeline to do it for you. So the first level, manual process, you do a lot of manual steps. As the end result, you get a trained model, of course, if the algorithm support it, and then you're getting to serve this model one or another way. And it's more like the responsibility of data scientists and a bit of machine learning engineer is to make sure that you get this trained model, and then there is a responsibility of operation people to serve this model. And that's where you go to production, and what you have for production is your prediction service, and it returns something meaningful to you, I do hope. The second step of the MLOps level is ML pipeline automation. So what's I try to do here, so you try to have a source code somewhere. It's a really good practice to have it. And then you try to pick up the whole machine learning pipeline and automate this pipeline and keep all this pipeline code in a source code. So in this case, if you need to deploy this pipeline in any of your environments, you can easily just take this pipeline. It will be automatically deployed. And this pipeline will take care about do all the steps and take care about the end result as a trained model. This model will be served and it will be properly monitored. And while it will be monitored, there will be some metrics defined that if you have a specific threshold passed, then you need to trigger, for example, retraining of the model. So that's more about the pipeline automation. And this third part is like the dream part of it. Maybe soon it will be not dream part anymore, but it will be fully CI/CD pipeline automation. And what's happening here, so you have specific sandbox where you do so-called orchestrated experiments. And in this case, that all steps that you perform, starting from getting data and getting the model back, you can orchestrate. And each iteration of the model will be written down. So you have experiments and you have runs, and each run will be logged in. Why it's important? Because sometimes you need to try different hyperparameters, and sometimes you can try, at least like 100 variations, and you want to get back and to make sure that if something went wrong, you can always get back to one of these experiments, to one of these runs, and pick up the right parameters instead of looking at them somewhere in the paper or laptop of your colleague. So you have the source repository, and your source repository knows that as soon as, for example, trigger, as soon as a merge with master of something, then you get the whole pipeline that build, test, and package your components, and then it gives you back an artifact. And this artifact can be a sort of an image, or it can be a library properly packaged. It can be different options. It depends of course, what you're going to deploy and how. And then you can move it with a release pipeline to the, for example, staging or pre-production environment, where again, exactly automatically start this pipeline, it will execute, it will return a model of your choice to the model registry, where each model get a version. You can use the same semantic versioning. And then you serve this model, and you have the prediction service that will constantly monitor and be triggered in case of some problems. And if you're working with pretty big models, that's the time where the feature store pops up. And in this case, sometimes it's pretty compute intensive to make some, to calculate some of the features. And sometimes it's really wise to make some pre-compute, store them in a feature store, and then just at the moment of serving, pick up these pre-computed features. So that's the whole CI/CD pipeline automation, when you don't need to care about each step, because it's fully, in the majority cases, fully automated. And it's the goal, because the more models you have, the more harder it is to manage your models. And the more models you have, sometimes you will go into build different pipelines that will be some sort of a combination of different models. Imagine that first you have a simple model that just running on the edge device. It's lightweighted model that do, let's say, the first step, and then if there is like the result, for example, in case of classification, it's classified as a fire. Just imagine we run an edge fire detection on the camera, then it will notify the bigger model somewhere in the cloud that will start it, and they will do it prediction. So that's a little bit about MLOps today. So what we learned so far. So if you want to maintain, if you want to deploy, if you want to test, if you want to properly monitor your model, you need to have some MLOps in place, machine learning operation. And different companies do it in different way, with the platforms, without platforms. And the majority of the cases, you just start with the manual steps, and then you see what you can optimize and make less manual work and less manual intervention. Think about, for example, starting the proper environment. If it's deep learning, that's in a GPU. If it's necessary, if it's standard machine learning, it can be just in a simple CPU with enough memory, of course. And then you can deploy it as a whole pipeline automatically. And of course, if the performance of your model is degraded, you can trigger automatically the retraining of the model. Or in case if you're working with the models, such as time series models, then you have another thing. Literally, for some of the models, you have nothing to save, because as soon as a new data comes, you need to feed the model again. Then it can look a little bit differently, but you always can automate it. And also, if you look at the whole picture of currently available ML infrastructure, you have a lot of moving pieces. And as I mentioned before, there is no one particular standard, but there are some agreed stages, and some of the stages can be fully automated, but the best case scenario when you can automate the whole pipeline. And maybe it sounds to you like you need a bubblefish for it. For those who didn't watch the Hitchhiker's Guide to the Galaxy, it was the unique fish. You need to put it in your ear, and it's translate in real time any languages in the universe to you. And if you want to communicate with another person really needs to have this bubblefish in his ear again. So I should say, don't panic. And I have this bubblefish for you, so we can communicate properly. And let's deep dive into the last section. Okay, so you heard today a lot. Heard today the basics of what is machine learning all about, what kind of roles do we need, why it's so hard to monitor, test it, and what extra steps should be taken to make sure that your model delivers something that is expected from it, and then you can be safe when it's in production. And today, because we don't have a lot of time, what I want to go through, I want to go a little bit about machine learning serving pipelines. From one side, you prefer to have one big pipeline that makes sure that you get from raw data to the specific values, and it's all running in production. But I want to concentrate specifically on this part. Why? Because what I noticed from my own experience for a lot of companies, it's actually important to separate these concerns. And what do you mean by that? Sometimes it's preferably to separate the training and the serving, because the requirements is completely different. For example, for training of the model, maybe you need a lot of compute, and for serving, maybe not. So my personal proposal in this case to separate them. So today we are gonna look through 3 options of machine learning serving pipelines. But before that, what is the machine learning serving pipeline? Remember, I was saying, think about the model as a function of an input, and that's a pre-processing, that's the data to make sure that they're digestible by the model with some pre-engineered features if necessary. Then you have the model that do your magic, this is an algorithm behind it, and then you have a post-processing. Because if your model deployed as a web service, so I expect that it will be JSON output, and maybe you want to use a JSON something more properly, and you don't want just return the JSON to your user. So maybe something different. Or if your model, for example, running somewhere in the background as a part of the ETL pipeline, and then you just need to write down the results to the SQL database, you also need some post-processing. So think about machine learning serving pipeline as a place where you can take your model, if it's possible to load this model, with a whole pipeline to do the data pre-processing and to get the post-processing of the data. So before I starting to think about deployment of any model, first thing that I want to try to understand, this is how end users are going to interact with this model. And based on that, I will think about different structure to do it. And I will start with, is it interactive or non-interactive use? And what do I mean by that? Whether the person directly interact with the model. Think about like machine translation, Google machine translation, where you send the text and you get the translation of the text back, this interactive usage, or non-interactive usage. For example, when your model runs somewhere on background and populate the SQL database, from which then the data go to the dashboard, for example. This is non-interactive usage. So it gives some specific concerns to deployment. Then are we working with a single record or are we working with a batch? And what's important here, because single record, single request, single prediction back. And if it's batch, I want to optimize the throughput, of course. Then it's also about synchronous or asynchronous. So in this case, synchronous can be example of deployment with Lambda, and asynchronous and can be example of batch. Because with case and synchronous, I should wait for response. It doesn't matter what. In sync with asynchronous, okay, I don't care. You know, I just go on. And then the last piece of it is, of course, do you want to use it real time or non-real time? And what do I mean by that? Non-real time, you're running predictions once per week as soon as a new data come in, and then just use it somewhere. And real time, when you want to use your model right now, for example, as a part of combination of real-time and non-real-time, is exactly a recommender system when you want to do some pre-compute, and then the real-time you want to return the predictions while your person is staying logged in at the website, for example. So today we'll cover briefly 3 flavors of model deployments. It will be batch serving, it will be online serving in real time, and the last thing will be the real-time serving with embedded model. So let's deep dive into each part. So the first will be batch serving, and it's really hard to share all the code with you right now. That's why in my slides I provided link. This is linked to the repo that's completely dedicated to this machine learning batch serving. So there you can play around and to see what you can do with it. So let's start with definition. What is a batch serving? What to optimize if you want to do batch serving, how end users are going to interact with it, and how we're going to validate the model, make sure that it's work as expected. So in case with batch inference, what do you want to do? You want to use data distributed processing infrastructure to carry out inference asynchronously on a large number of instances at once. And when I'm talking about batch, it can be millions and billions of predictions. So in this case, what to optimize, of course, is throughput. It's not latency sensitive. And in this case, the probability that end user will directly interact with it is pretty low. In the majority of the cases, user will interact with the predictions that are stored somewhere like in a data storage as a result of this particular batch jobs. And the validation will be offline. So, and in the majority of the cases, you're gonna use this. You shouldn't spin up a separate web server. You shouldn't spin up, let's say, a lot of instances of it to make the specific prediction. You can just say, okay, I know that I get this data from all the sources this number of time, and I know that I have some specific schedule, and I have time. I'm not in a hurry to process this data and add them. That's a little bit more about batch inference. And as I said before, the majority of the use cases will be the batch inference. The second is as online serving near real time. And why I'm saying near real time, because here we talk about micro batches, but not about direct streaming. It can be different, but for now, let's dive in. So as well, there is a link to play around with machine learning online near real-time serving. So what's this all about? First of all, what is online inference and why it's so important? So online inference is about responding with a prediction to the request of the end user with a low latency. So in this case, what do we want to optimize? We want to optimize latency. If the person that visits our website and we are getting the recommendation too late, they will be not used by a person. Imagine that person is scrolling, I don't know, wear like shoes or something. Then 1 week ago, scrolled about the different like dresses. And if you're going to show this person dresses, probably that's not what this person wants to see right now. So in this case, end user usually interacts with the model directly available through an API, or just in case, it can be as well like a machine translation example. Imagine that you're the Google translator, you send a piece of text, and if you need to wait for ages, the chances that you will stay at this website or use the service is pretty low, so we'll leave it. And in case of validation, what are you going to do? You're going to do a mix of it. You're going to do offline validation and as well online validation using A/B testing. And that's the majority of the cases where you're going to use it. If you need to serve, let's say, to thousands to almost thousands to some millions requests, that is good. But if you want to serve more, then probably there's a way to think about batch inference, because maybe it will be better. And in this use cases, as I mentioned before, you interact with the model directly and model exposed as an API. So in this case, if you're using, for example, web services endpoints available on the cloud, you can manage it easily, you can scale it easily, and you can scale it up and scale it down in case of necessity. So that's will be the majority of the cases that we're going to use it. And exactly right now, if you're looking at the proposal that is available on the cloud, almost all of them are about deploying your model as a microservice and interact with model, getting the ready endpoints. And now we are moving to the last part, and it's the most interesting one, for me at least, and it was real-time serving with embedded model. And that's exactly when we talk about working with streaming data, and that's where you're so sensitive to the latency that if you're gonna send request to and get predictions back from the model, it will be too late. So in this case, what it's about, so real-time serving with embedded model is about distributed event and time processing with millisecond latency and sometimes high throughput. So what to optimize here, first thing is latency, but throughput is important as well. Usually end user will not directly interact with the model, but the user will be directly interact with the application. And the validation here as well offline and online via A/B testing. And then the code can be followed through the link. And here I think the most interesting part. So that's exactly when you embed your model into the, for example, Kafka application. So the link to play around is here. And that leads us to the end of this story. So thank you very much for your time. I do hope that it will help you to help your company to deploy the model for the first time, or at least to know how to redeploy models if they were not deployed properly. And you know for which use case you can choose the proper deployment, batch of online serving near real time of the embedded model. Hey, I'm pretty sure that now I have a lot of questions. So there is my LinkedIn link, and you can ask all of them here.